Okay, last one. You ready? This is it. You ready? Keep going. Until you're finished. You'll be happy you did. Okay, so we need to use two different parts of our brain. We need to have an ionic part of our brain and a covalent part of our brain because there are different rules for how to write formulas and name compounds using ionic and covalent compounds because for our purposes, for the most part, they have different properties and they react in different ways. So it's important that you understand or be able to classify compounds as ionic or covalent. So let's look at them. We have copper 2 sulfate. We say, oh, a metal, an 8, that ATE ending. Where do I know to look for that? I look on table E. That's a polyatomic. I know that's ionic because we have the metal and the metal and nonmetals together. Here we have two nonmetals. That's going to be covalent or molecular. Here we have metal and nonmetal. This IDE ending implies that there's just one nonmetal. Other than hydroxide and maybe one other exception, for the most part, you can count on the fact that if it has an IDE ending, the second element is only going to have, be a single element and not a polyatomic ion. And because it's a metal and a nonmetal, that's ionic. Here we have a metal and a nonmetal, that's ionic. Here we have two nonmetals, that's covalent. Let's do the ionics first. We see that the first one says it's copper, so we write the symbol Cu. It has a Roman numeral 2. That Roman numeral corresponds to the charge. Notice that copper, if you look on the periodic table, can have a +1 or a +2 charge. Well, how do I know? Is it the +1 or the +2? It's the +2 because it's copper 2. Then sulfate, if you look on table E, is SO4 with a -2 charge. Cross out the charges, crisscross the numbers, and you'll notice that 2 to 2 ratio is not in lowest terms. Because this is an ionic compound, we need to reduce, so we realize that our formula is CuSO4. Let's look at sodium sulfide. Sodium is Na with a +1. Sulfide is S with a -2. Cross out the charges, crisscross the numbers, you get Na2S. Finally, we have FeO. Now, we need to write the name of FeO. So I write the name of iron first, the cation, and then I write the name of the anion second, oxygen. And remember, if it's only one single element, I change its name to IDE. It got married. Isn't it cute? Oh my goodness. But I have a problem. Iron can have either a +2 or a +3 charge. How do I know what charge this iron has? Well, oxygen has a -2 charge. We know that because we can look it up. It's in group 16. It wants to gain 2 electrons. And iron and oxygen in this compound are a 1-to-1 ratio. So we know, is it the +2 or the +3? Well, in a 1-to-1 ratio, it has to be +2 because 2 to 2 would be 1-to-1 ratio when you reduce it. So we have to identify this iron as iron 2 using the Roman numeral oxide. This comes up a lot on tests where they'll give you something like this, XCl2, and they'll say, what group are you going to find X in on the periodic table? Well, the easiest way to do this is to reverse the crisscross that we did up above in order to form the ionic compounds. Positive always comes first, the negative comes second. There's a 1 subscript here, bring this up, it becomes a -1. The 2 subscript down here comes up, becomes +2. So we have to look up, we have to make sure that chlorine does have a -1 charge, which it does. So we realize that this X must have a +2 charge, which means it's probably in group 2 of the periodic table. Okay. Making the switch to the other side of our brains, we are looking at covalent compounds. Now, covalent compounds, no need to crisscross. There is no crisscrossing involved. Here, prefixes are going to tell you the whole story. So here we have 1 nitrogen. So we just write nitrogen. If we only have 1 atom of an element, of the first element, or 1 mole of atoms of the first element, however you want to look at it, we only write nitrogen. We don't use a prefix. But for the second element, oxygen, we have one again. Now we have to identify that we only have one. So we write monoxide. Mono stands for one. Carbon dioxide, okay, is our other covalent. Carbon, we write C, dioxide, O2. Di means two, tri means three, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10. Okay, now there will probably be a question that asks you to find a compound that has both ionic and covalent bonds. Well, if I look at the ionic compounds, this one has the iron 2 oxide has a metal and a nonmetal. It's only ionic. And sodium sulfide has a metal and a nonmetal, only ionic. But if you look at copper sulfate, it has a metal and a polyatomic. The polyatomic consists of two nonmetals. Those two nonmetals are bonded together covalently. So it contains an ionic compound between the copper ion and the sulfate ion, and then a covalent bond between the atoms in the polyatomic ion. Okay. All right, so we talked about bonding, about ionic bonding is a transfer of electrons from a metal to a nonmetal. Just really quickly, you should know a few things about ionic compounds. You should realize that you should think about the fact that you've never seen melted salt. I always like to use NaCl as our example compound. We tried to melt it in the lab. It didn't melt. Because it doesn't melt, most ionic compounds, it's very difficult to break the attraction between the positive and negative ions, so they have very high melting points. But they're also soluble in water. We'll talk about why in our next couple of units. And when they do dissolve in water, the ions that are held together in the solid state, they separate or dissociate. And in the water, or also when they melt, so either in an aqueous solution or when they're molten, which means melted into a liquid state, they're going to have moving ions. When they have moving ions, that means they have moving charged particles. You realize that if they have moving charged particles, they're going to be able to conduct electricity. Covalent compounds. Now, the hardest part about covalent compounds is understanding the difference between a bond and an intermolecular force. Now, covalent compounds, the examples I would use, carbon dioxide, water, sugar. This is glucose, by the way, not sucrose. Realize that this is a gas at room temperature, carbon dioxide, water is a liquid, sugar is a solid. So molecular compounds tend to be soft solids or liquids or gases. If they're a gas at room temperature, that means they have low melting points. Sometimes they're soluble in water, sometimes they're not. Depends on if they're polar or nonpolar. And they don't conduct electricity. Why? They do not have moving charged particles, of course. Now, here's what I want to show you. I'm going to extend this page a little bit, and I'm kind of going to draw this myself. Okay, very important what you need to know here. Let's take water, for example. Okay, I'm going to teach you how to draw these dot diagrams if you forgot later on. But for right now, I'm going to draw it myself. Now, this bond represents a shared pair of electrons, right? A shared pair of electrons. And that bond can either be polar or nonpolar. We determine if it's polar or nonpolar if it, sorry, hold on a second. We determine if, sorry about that. We determine if it's polar or nonpolar by taking the difference in electronegativities. We look up the difference in electronegativity between oxygen, which is 3.4, and hydrogen, which is 2.2. Yes, 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 you guessed it, table S. We're looking on table S, and we have to subtract them. So we go 3.4 minus 2.2 gives us a value of 1.2. What does that mean? Well, if you have a value, an electronegativity difference between 0 and 0.5, you can say that the bond is nonpolar covalent. If it's between 0.5 and 1.6, you can say the bond is polar covalent. And if it's 1.6 or greater, you can say the bond is ionic. Okay? So how do you determine if a bond is polar or nonpolar? You subtract the electronegativities. Now, that's bonds. Forces, intermolecular forces, are the forces between molecules. So let's say I have two water molecules. What keeps the water molecules together so that they can be a liquid that we can drink that can quench our thirst? Well, this oxygen is kind of like a bully. It's pulling the electrons away from hydrogen, so hydrogen's feeling a little sad at the moment. Hydrogen sees that there's this lone pair of electrons sitting on a neighboring oxygen, and there's a brief attraction to that lone pair of electrons. This right here is called a hydrogen bond, but more importantly for right now, it is an intermolecular force, or an IMF. There are three types of intermolecular forces. There's hydrogen bonding, there's dipole-dipole, and there's dispersion. Dispersion forces happens between nonpolar molecules. How do you determine if the molecule is nonpolar? Well, we know how to determine if the bond is polar, but now we need to determine if the molecule is polar or nonpolar. So let's look at an example of chlorine. This is Cl2. So we have two Cl2s. We look at the molecule as a whole, and we see, is the molecule symmetrical or asymmetrical? That's SNAP. We see that the molecule is symmetrical. Picture an electron cloud. The electrons are evenly distributed throughout the molecule. It's symmetrical. That means that the molecule is nonpolar. If it is nonpolar, it doesn't have a positive or a negative end. So it has very difficult time to attract another nonpolar molecule. How do you get it to attract? You have to make it very cold or under high pressure. Why? When they get close enough together, then there's more of a chance that they will attract. Dipoles is a little different. Dipoles, you have one atom that pulls the electron away from the other. It gives them a partial positive and a partial negative charge. Oops. Here you're going to have an attraction because the partial negative is attracted to the partial positive. This is a stronger intermolecular force. This is the weakest. You can just identify it as the weakest. Or you can say it has weak intermolecular forces. Hydrogen bonds is the strongest. Why? Hydrogen bonds occur between molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen. Look in particular for water, ammonia, or hydrogen fluoride. Those molecules are very polar. Because they're very polar, they are going to have the strongest intermolecular forces. Okay, almost done. Ready? Okay, this is a summary of what we just said. Talking about nonpolar covalent, polar covalent, and ionic. We're going to draw these structures in a little while. Okay, and this is a summary of molecule shape. Remember, SNAP will tell you This is polar. Why is it polar? Because it's not symmetrical in either direction. Don't get trapped. Water is polar. It's asymmetrical. Okay, these molecules over here, CCl4, that's symmetrical. You can fold it onto itself in either direction and it's a mirror image. It will fold directly onto the other side. It's symmetrical. So that's nonpolar. Remember SNAP. Symmetrical, nonpolar, asymmetrical, polar. Same thing with carbon dioxide. Okay, metallic bonds. What are metallic bonds? Metallic bonds we already talked about. The most important thing to remember about metallic bonds is how do you recognize a metallic bond? You're looking for one single metal. For example, what holds atoms of gold together? Metallic bonds. What holds atoms of copper together? Metallic bonds. Cobalt. Metallic bonds. Then, why are metals good conductors of electricity? Because they have a sea of mobile valence electrons. Network solids. What's important to know about network solids is there are three important ones. Carbon, that's a diamond. Carbon, that's graphite. Notice that they're both carbon, but they're bonded together differently. That gives them different chemical properties and different physical properties. You wouldn't trade your diamond for a pencil, would you? Well, no. Why not? Because they have different properties. Also, SiO2, which is quartz, silicon dioxide, it's the stuff sand's made out of. That is also a common network solid. All of these, what they share in common is that they are very strongly bonded together. The network creates that makes them very strong, so they have extremely high melting points. Finally, how do you draw Lewis dot structures? And keep these words in mind. Atom. An atom is the simplest unit of an element. It is one atom of oxygen. An atom of oxygen has 6 valence electrons. Go around in a circle. That's how you draw the Lewis dot structure for oxygen. A diatomic element or a molecule. If they ask you to draw a molecule of oxygen, that would be different. You would have 2 oxygens. You would have to put 6 valence electrons around each. Then the unpaired electrons, you would have to pair up from each atom. Finally, an ionic compound. Remember, it's electrostatic attraction that holds an ionic compound together. That means the sodium loses an electrons and becomes a positive charge. The chlorine's going to gain electrons. When it gains electrons, it's going to have an outer shell of 8 electrons. It had 7. It gained 1 from sodium. You have to hug it in, and you have to write that it has a -1 charge. Why a -1 charge? Because it gained an electron. Notice that +1 and -1 add up to 0. And that means the reason they bond is to become more stable. One loses what the other gains. Hope these sessions were helpful for you. Good luck. Don't forget where you're going. Come in, email if you have any questions. We look forward to working with you. Oh no.